Hello everyone. Till the last video, we have built a clock tree for a 16 clock endpoint circuit, and we came up with certain specifications for that particular clock tree. For example, we came up with some values of skew, we came up with a latency number, we came up with the power number, we analyzed pulse width violations, we analyzed duty cycle, and so on. We did all these things, and the question that we were left at was that was that the best that we could have achieved, or can we do something better? By better I mean, can we use lesser buffers, so that by using lesser buffers, if you reduce the amount of buffers that you have used in your circuit, you reduce actually that directly impacts the latency and the power number. So we have to identify some parameters from the existing clock tree and existing numbers, so that we can do something, we can do an optimization of the clock tree itself and arrive at some specific numbers of buffers that we can use for the clock tree. So let us try to do that. So for that, what we'll do is we'll look into the clock tree that we have already built. So this was what we had. We had a clock tree. We had this complete clock tree. The clock paths had like 39 number of buffers it was using, and the latency, the highest latency that we saw was 9 buffer delays and 10 wire delays. Basically the latency remained the same because because the spread of the clock endpoints was very even, was very periodic. So the latency number is constant, so highest and the constant is the same, and it was 9 buffer delays plus 10 wire delays, and the total power that we had was 39 multiplied by the dynamic power. This is the dynamic power component, this is the short circuit power component, this is the switching activity, and this is the leakage power component. So we had all this with us, and we had given a yellow tick for latency and clock tree power. Why so? Because we had a point over there that can we do something better than what we have now. So let us try to look into identify some parameters that we can work on to achieve a better power or better latency number. So we have this equation with us, we have latency and we have the power number. So out of this equation, can we find out some parameters that we can tune to, or then that we can play with, so that we can eventually arrive at a solution that yes, like instead of using 10 buffers, you can actually use 5 buffers. So can we arrive at that solution based on what equations we have with us? So let us try to look into the terms one by one. So first is the load capacitance. C is the load capacitance, and load capacitance does play a major role. So it's like higher the load capacitance you have, you will there is a problem that the delay of that particular clock cell will increase, and vice versa. If the load capacitance is lower, the delay of the cell will be faster. So what load capacitance what actual value of load capacitance are we looking at? Are we looking at a very high value? Are we looking at a very low value? Because by the way, load capacitance directly impacts the short circuit current and other kinds of power, basically the dynamic power over here will immediately get reduced. So and the leakage power also is a function of the load capacitor, which we will be looking in some time from now. But hearing the load capacitance can have, or at least looking into the load capacitance number that we have now, we can come up with some conclusion. So it looks like we can tune this particular thing, the load capacitance thing, and which can directly impact the P total. As you see that the total power is proportional to the capacitance or proportional to the load capacitance. So looks like we can touch this parameter and we can do something about it. So we have to understand, we have to study what can we do about it. So let us first bring out that particular parameter, that particular checklist that we can touch. So capacitance or the load capacitance is the one that we can touch, that we can tune, and we can come up with some solution, some optimal way of building the clock tree, or of building a better clock tree. So this is one parameter out of it. Second, we have the voltage. So this is the supply voltage. This is basically the VDD that is being given to the complete chip. there is a way that we can reduce the supply voltage, but this happens only at the board level. Right now what we are talking capacitance that we can modify is at the circuit level that we can do something. But at the board level, yes, there is a way you can always reduce the supply voltage VDD over here, and so that will impact directly this equation. This complete equation will get modified, because if you see the total power is a quadratic function of the voltage. So as you lower down your supply voltage, that directly impacts the total power, and that's a huge power save for us. But again, with this power saving comes something else. So if you reduce the voltage too much, it will impact your noise margins. So we'll look into the noise margin thing later section, in the later sections. But right now, if you see, voltage is a parameter that is available for us, which will, so without even doing anything, without even touching any of the clock tree buffer or any of the clock tree wire, if you just tune your voltage, if you just reduce your voltage, you see the direct impact is on the power. But again, if you reduce your voltage, there are other issues that can lead to. So for example, delay is also a function of your voltage. So as you reduce your voltage, the delay will be a bit slow. The buffer delay will be slow. We will look into how the voltage directly impacts the buffer delay. We'll look into that. So it's basically so let me brief you about this. It's basically about the drain current equation. The drain current equation is a function of the voltage. So that's how it modifies the delay. But we'll not get detailed and get deep into that. Let's keep it at the brief level. But again, the voltage, the tuning of the voltage to get a better power number can be achieved at a board level, but not from a circuit level point of view. But we are looking for some parameters over here in this particular checklist that can help us from a circuit level point of view. So voltage is not a parameter that we can tune at this point of time. We'll look later how can we tune the voltage to get certain functions or certain parameters of the circuit working. So let's keep the voltage aside for some time now. Again, this is the next parameter is the voltage, which is again the supply voltage. Next we have the short circuit current. So remember, this complete term was related to the short circuit power. V was the voltage, I was the short circuit current, and T was the time period for which the NMOS and PMOS were turned on. So this is that particular equation that we had. So short circuit current, yes, there is a way that you can reduce the short circuit current. So if you look into the basic fundamental of current, there is a current flow. When there is a current flow, whenever we have a potential difference between point A and point B, we see a current flow. So using that concept of current, that basically current flows from high level to low level. In a layman term, the current flows from high level to low level. So basically there is a potential, there is a point A which is at high potential, where there is a point B which is at low potential. Now there is a potential difference between A and B. That's why we see a current flow. So is there a way that we can control the potential difference between points so that we avoid the flow of short circuit current, so that we control the short circuit current? Is there a way? So right now what we are seeing, the potential difference between the VDD and the ground is basically VDD, because it's completely short circuited. The NMOS is on and our PMOS is on. But can we do something with the load at the output of the CMOS inverter that can tune this short circuit current? That can basically we are looking for a zero potential difference, so that this short circuit current value can be reduced. So can we do something about that? We have to look into details of that. So but let's put it in our checklist that we will be looking into short circuit current value, short circuit current parameter. Basically any kind of current, if you are able to get a potential difference, if you are able to get a low potential difference, basically close to zero, you can avoid a current, you can avoid a current flow. So let's look, we will be looking into the short circuit current from this angle also to reduce the power. Next we have the switching activity. The switching activity is again from the that is again something that comes from a design point of view. It is not at that we can do something at the circuit level, but it is again from the design point of view. So this is not in our hands. Definitely it's not in our hands. Next we have the supply voltage, which we talked about sometime earlier. Next we have the leakage current. So leakage current, again, it's a current that flows in the whenever your NMOS and PMOS are off. And by off I mean the gate to source voltage of your NMOS and PMOS are less than threshold voltage. So is there anything that we can, so again if the threshold voltage of the gate and the source is a bit high, right now we are using the NMOS transistors that we are using. Those are basically a nominal threshold voltage devices that we are using. What if we increase the threshold voltage? What can happen, and how can that impact the leakage current? So again, this is again a parameter that is available from a circuit point of view. So let us try to put the leakage current also in our checklist. So we have completed this equation, and since I'm running out of time, what we'll do is we'll look into all this one by one. Basically we'll start from basics again, not too basics. We'll look into the inverter circuit and see how can these three could be achieved, and that can eventually result to a conclusion that we would be saying that yes, we can use a lesser number of buffers, we can reduce the capacitance in so and so way. So let us try to look into all those things in the next video. Thank you.